Okay, let's continue with LiDAR returns. So the X, Y, Z coordinates of each return is calculated using the location and orientation of the scanner, the angle of the scan mirror, and also the range distance to the object. So X, Y here are latitude and longitude, of course. It's the location of the data point on the surface of the Earth. Z is the distance between that location and the sensor, right? Since we also know the altitude of the sensor, we use the difference. We use the difference between the altitude of the sensor and the distance between the, 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 the data point and the sensor to address what? To address the elevation of that data point, right? So the collection of returns is known as a point cloud because when a sensor finishes scanning a specific area, it will receive a lot of data points. And if you put all those points together using their geographic coordinates, you will get something like this. So we have a lot of points here, but they are colored in different hues, right? So I can tell you that this LiDAR image is covering a specific river here. That's the left bank of the river, that's the right bank of the river, and here is the river bed, the green and the blue area. And I think some of you may have noticed that these different colors, they are representing different elevations. Red, yellow, and orange, they are representing a higher elevation. So on the left side of the river, on the right side of the river, we have banks. These points, they have higher elevation compared to all those points at the bottom of the river or other points within the riverbed. Okay. And let's talk about resolution now. The resolution of LiDAR is different from resolution or spatial resolution of other optical remote sensing techniques. The resolution of LiDAR is described by the number of pulses per unit area or by the minimum angular resolution. So it is determined by a lot of factors: aircraft speed, flying altitude, FOA, and rate of pulse emission. And higher resolution and a narrow FOA are better, right? They are needed to penetrate dense vegetation. And although you can have higher resolution with narrow FOA, the data you have will be more accurate. But the problem is that you will need to have a larger space for data storage because the LiDAR data can be very huge, You should be careful with that. And dealing with them is even more difficult than saving them, than storing them. Okay, you need a very powerful computer to deal with, to process large LiDAR data set. And let's talk about the intensity of returns or the strength of returns. It varies with the composition of the surface object reflecting the laser pulse. It means that different objects, they reflect they reflect laser energy, laser signal at different efficiency. LiDAR intensity is the reflective percentages of the surface objects. It can be used to identify land cover types because some of the land cover types, they reflect a lot of energy. Some of them reflect only a little bit. So according to different reflectance, we can guess the specific land cover type that reflected this signal, this return. For example, here is a list of different typical materials and their reflectivity for LiDAR signals. White paper it reflects almost 100% energy from LiDAR signals. The reason why paper is white is because that it reflects almost all visible light. Snow is also bright, 80 to 90%. Then we have beer foam, different types of trees, dry sand, white sand, and clear water. You can say it only reflects less than 5% of LiDAR signal. So in a LiDAR image, clear water will be pretty dark because you can barely receive reflected energy from clear water. And the snow will be pretty bright because it reflects most LiDAR beam or LiDAR signal energy. Okay, so I'm not asking you to remember to memorize the reflectivity of all those typical materials and land covers, but at least you should know that from the brightness of an object, you can generally tell the reflectivity of it for visible light. And pre-processing, it means that the processing happens in the field, on the plane. I think I mentioned before that there is always a computer system connected to the sensor in the field, and this computer system can do some pre-processing. Data collected by the onboard computers are in formats decided by the system vendor, which means different LiDAR sensors, different producers of them, they have their own data format, raw data format, for, of course, for their business benefits, right? And the multiple flight lines are firstly calibrated. You saw the flight plan figure before, right? There are usually multiple flight lines, and there will always be overlap between lines, right? Different lines are firstly calibrated, error values and noise are also filtered. This can be done by onboard computers. And returns are classified and separated by a category: first returns, second returns, last returns. You should also know that the last returns, they are usually bare earth returns. Okay. And also, point data is usually delivered by vendors as either ask-to or in LAS format. So when they are selling you data, the data format they provide is always, not always, usually ask-to or LAS. Ask-to is simply the easiest text file format. The TXT file you always use in Windows is actually a format of ask-to. Just text, okay? LAS format is another story. It's an industry standard binary format for storing airborne LiDAR data. So it is not for a specific company or enterprise. It is a commonly used format. It maintains information specific to the LiDAR nature of the data while not being overly complex. And this format is maintained by ASPRS. And this format is free, is for free, so everybody can use it. And we can use different software to deal with LiDAR data. And the yearly processing steps, there are 3 steps. The first step is import raw points into a processing software, point cloud, right? Each point is representing a specific return, right? And then we convert point cloud to a triangulated irregular network, TIN network. And then from TIN network, we create raster file. So here, example. So this figure shows you the raw data points. Each yellow point here is a raw data point, right? Because some of them, they are within the area of vegetation, right? Some of them, they are along the roads, right? This is a road, this is another road, and we can see a lot of building roofs. But for this specific example, obviously, the author was not interested in the elevation of buildings. I mean, that's the reason why there is no returns from the top of all those buildings, right? All those yellow points, some of them are on the boundary between buildings and the surrounding environment, but yeah, very limited number, okay? So second step, transform all those data points into team network. Basically, you connect all those data points to create a lot of small triangles, and from the shape of these triangles, and you can find out, you can create this network, and each data point is a node instead of a point inside this team network. And also the slope of the triangle size and face are therefore known. So you have this skeleton for raster data file. So for that specific example we saw before, the left side is the raw data imported to your PC, yellow points, right? On the right side, we have team network of the image on the left, right? We can see a lot of small dots there, small triangles. You cannot even recognize them, but we can see huge triangles here, right? Here on building roofs. That's because there is no data point on these building roofs. So that's why we have huge triangles. So next step, create a raster model. Okay, raster data eventually stores elevation values in a regularly spaced series of uniform data units called pixels. So in team network, the distance between any pair of data points is different. So if we randomly choose two pairs of data points, the distance between each pair of points usually is different, right? But in a raster data file, you need to create a regularly spaced series of pixels, which means we need to do something called interpolation. Okay, but before that, let me introduce two types of raster models, DEM and DSM. DEM is digital elevation models, raster-based models of the surface of the Earth. DS model is the raster-based models of features above the surface. For example, if there is a tree standing there, DSM model gives you what? Gives you the elevation of the top of the tree. DEM gives you the elevation of the surface that tree is standing on. Okay, this is DEM. It is trying to provide information about the surface of the Earth. This is DSM. We have a lot of small spikes here compared to DEM. That's because DSM is usually produced by the first returns. The first return, for example, for a tree, is usually produced by the top of the canopy. That's the reason why I told you that DSM is giving you the elevation of the top of the tree instead of the elevation of the surface that tree is standing on. Okay, so that's DEM and DSM. Okay, and how to create a raster model. Raster data can be created from team models by interpolating the elevation values for each pixel center using linear interpolation. Like I mentioned before, all those data points collected by LiDAR systems, the space between them varies from one pair to another. This is not something we want. In a raster data file, we want evenly spaced pixels. Okay. So the minimum raster resolution, or in other words, the size of the area represented by what? By a pixel. By a pixel. Depends on the LiDAR return resolution. So at least there should be average of 1 pulse for each pixel. Within each pixel, there should be a return. So here is the relationship between what? Between point density. This is the resolution for LiDAR data, and the point spacing, PS. This is the resolution for raster file, right? PD, for example, 8 pulses per square meter. For raster data model, the resolution is in meter or even kilometer. But if the resolution is 0.6 meter, it means that each pixel in this raster data file represents a 0.6 by 0.6 meter area in the real world. So here is the formula to address the relationship between point density and the point spacing, okay? So here is the team network, right? All those points, they are irregularly distributed within the space. Here, we want to transform it to this raster data model. Can you see those red dots? Each one represents a center of a pixel. And those red dots, they're evenly distributed, evenly spaced within the space. Okay, so you need to use known value, which means the values collected by LiDAR sensors, to interpolate the values for red dots to eventually have this raster data file. Okay, so here is the result. According to the interpolation, now each red dot has a specific value, right? You can say each dot here has a value. And then you can use this raster file to produce DM or DSM, to produce 2 different types of products. Okay, so how can we produce height images? You calculate the difference between DSM and DM. In other words, you know the elevation of the top of the tree. You also that is provided by DSM. You also know the elevation of the surface that this tree is standing on. That is provided by DEM. If you calculate the difference between them, then you have the height of the tree. It's just that simple. So a DSM minus DEM, then we have feature heights. You can consider a tree as a feature or any geographic object or entities on the ground as a feature. So here, raster model feature heights is the difference between DSM and DEM. Yeah, here is a larger size of the feature heights image. So because LiDAR data provide elevation, we can produce hue shades like this, right? For example, here we can say that there are shadows and bright side. I mean, or bright side and dark side for a specific mountain, right? That's because that we can arbitrarily decide the position of light source, usually illuminating from the northwest, top left corner of this image. If the light source is here, it's naturally that all those mountain sides facing the light source, they are bright. The other sides of mountains, they are dark side, and dark side. Because we have light side, and dark side, we have shadows, we have this perception of hue shades. This is actually another type of 3D geovisualization, right? We can say this is a mountainous area. Here we have a river. Here we have a river. Could be a road, could be a river because it's very linear. But according to this image, right, we can be sure here is a river because we have bridges connecting 2 sides of the river here. They're all clues. It's like a detective game. It could be a river, it could be a road, but we have linear features across this, another other linear features crossing this linear feature. Then you can guess there must be bridges and crossing rivers, crossing a huge river. So here, this linear feature here is a river, and the other side of the river is the urbanized area. It's very flat, and we can see small squares. Each one is a block. Each one is a block. So yeah, on the left side, it's a hue shade from DEM data. On the right side, it's a hue shade from DSM data. We can see more shadows because in this image, we have trees, we have buildings, right? We have bridges. They all produce shadows in hue shade images. And of course, we can create contour lines because again, it's elevation, right? This is a contour contour line map of the same image I showed you multiple times before, right? And more examples here. This is a high-resolution multi-beam LiDAR map showing spectacularly faulted and deformed seafloor geology. This is a crater, right? This is the center of the crater. This is the circle of the crater Okay. And here another image. So this is a real color picture of a bridge. This is a this is a LiDAR image taken when the sensor is flying toward this bridge or away from the bridge. And this is a LiDAR image when the sensor is flying over this bridge. So this is a bridge, right? And here is a mountainous area, a small mountain or hill, because usually we use warm colors to show high values, and high values here represent what? Higher elevation. So here we have a mountain, right? And another small mountain here, and here is the river or lake. I think this is a lake or ocean, I'm not sure. It's called Bixby Bridge at Big Sur in California. I think this is a river, right? This is a river, this is an ocean or the lake. And more examples. Here is another animated example from YouTube. You can use the link here to watch it. And in entertainment industry, in movies, the concept of LiDAR has also been portrayed in a very fancy way. So here is a movie, I like it very much. It's called Prometheus in 2012. All these scientists, they released these small drones, right? Each drone is emitting laser signals to the surrounding area to scan the internal structure of a mountain. Here is the result. You can say here the blue area is outside, is portraying the outside of the mountain. The green area is the inside of the mountain, surveyed by these small, cute drones. And you can say there is huge halls here, here, and here. There are tunnels, spiral tunnels here inside of this mountain. There is something like a well, like a launch well or something. Obviously, when you have the distance data, you can address 3D environment like this, right? For all those small drones, if they detect the distance between itself and a specific point on the wall of this tunnel, and if it repeats this thousands of times or even hundreds of thousands of times, you have this detailed inside structure of this mountain, right? And here is another example from Iron Man 3. Okay, in 2012, same year, Tony Stark here is trying to rebuild a crime scene or something like that using this 3D environment. And it looks like LiDAR because if you are standing somewhere inside of this thing and you know the distance, you get the the distance data of surrounding environment, you can easily build a virtual environment like this. And here is another tool you are going to use in your lab. I'm not going to detail here, but in the next slides, you can find out how to use this QT radar. It's called Quick Terrain Radar to rate and to view and to do some limited operations on your LiDAR data. This is for free. QT Radar is for free. QT Modeler is not for free. QT Radar, we have it on your lab PC, on our lab PCs in Derby 135 and 140. You can use it there, or you can download from the website of this company. Okay, so yeah, you can say here I have listed some steps about how to view the model data and how to use some very basic functions. Okay, that's all for LiDAR. That's all for LiDAR. Thank you very much.